In this video, we're going to compare the differences between CPUs and GPUs. Let's jump in. The CPU, or central processing unit, is often called the brain of your computer. It handles nearly all the processing work required to keep your operating system and software running smoothly. One of its key strengths? Low latency, meaning it can process tasks very quickly, but typically one at a time. Inside the CPU, you'll find first the arithmetic and logic unit, or ALU. This handles basic operations like addition, subtraction, multiplication, division, and logical comparisons. It's essential for most of the calculations your system performs. Next, we have the control unit. Think of it as the CPU's traffic cop, directing data between the CPU, memory, and other components. Then there's the cache, a small but super fast type of memory. It stores frequently used data and instructions, and it works alongside RAM, or random access memory. While RAM isn't built into the CPU, it's crucial, serving as a workspace for the CPU to quickly access the data it needs. Modern CPUs often come with multiple cores. You've probably seen processors labeled 8-core or 16-core. That means they have multiple processing units that can handle tasks independently. This enables parallel execution, multiple operations happening simultaneously. It's a game changer for multitasking and modern applications. Now let's shift gears. As software graphics and animation became more complex, CPUs struggled with the intense demand. Just picture a video game rendering thousands of moving pixels, each with its own color, brightness, and motion, all in real time. That's what gave rise to the GPU, Graphics Processing Unit. GPUs were initially designed for rendering graphics, but they've evolved into powerful parallel processors. They still share some components with CPUs, like ALU's control units and cache, but their architecture is fundamentally different. What sets GPUs apart? Massive parallelism. They're packed with hundreds or even thousands of small cores, optimized for repetitive operations across large datasets. This makes them ideal for tasks like image rendering, simulations, and machine learning. Today, GPUs power far more than just graphics. They're used in artificial intelligence, financial modeling, scientific simulations, video editing, and much more. CPU versus GPU. Quick comparison, function. CPU, general purpose processor for a wide range of tasks. GPU, specialized for high volume, repetitive computations, processing approach. CPU, serial processing, one task at a time. GPU, parallel processing, many tasks at once. Design, CPU, fewer but high-performance cores. GPU, more cores, each handling simpler jobs. Performance focus. CPU, low latency, quick response. GPU, high throughput, bulk processing power. Use cases. CPU, browsing, operating systems, general software. GPU, AI, simulations, video rendering, scientific computing. So, can a GPU replace a CPU? Not quite. GPUs are powerful, but they are not built to replace CPUs. They're built to work alongside them. Think of them as teammates. The CPU handles general logic and decision-making, while the GPU tackles the heavy-duty parallel tasks. Final thoughts. CPUs are best for sequential tasks, handled one at a time with precision. GPUs thrive when handling massive parallel workloads quickly and efficiently. Thanks for tuning in. If you found this breakdown helpful, give it a like, subscribe, and check out the channel for more in-depth tech guides and up-to-date interview prep.